All right, hello class, and welcome back to the fourth part of this lecture. In this last part, we will somewhat briefly, I hope, go over some of the sort of tie up some loose ends that we didn't quite cover in much depth earlier on, and we won't honestly cover in much depth now. But I'll just give a few examples, right, to illustrate these kind of issues. So specifically, if you remember at the beginning of this lecture in part A, we talked about several sort of pernicious sources of modeling error and uncertainty in our model. We qualified those in several ways, right? There was parametric, and I think we've focused on that throughout this lecture for the most part. I mean, so this is sort of the main theme of the parts B and C. However, right, as I mentioned earlier on, there are sort of other harder to deal with cases, and some of those are structural errors in the modeling. So basically, you assume the model is linear when it's not, and of course, all real models are nonlinear. If you may remember, I gave an example of saturation as a source of nonlinearity. We also mentioned unmodelled states, and that's something we do deal with to some extent, although we haven't dealt with it very much in this lecture. So higher order dynamics, unmodelled states. And, well, those are the three main ones we want to cover. The other one is sort of a special case, which is time-varying structural parametric uncertainty, and time-varying errors and so forth. In this slide, I think we I forget how we color-coded them, honestly. I think that was pink maybe, and parametric was that, and maybe the other structural was orange or something. Anyway, so we're doing the orange one, which actually I don't have a color for. Right, so structural modeling here. And this isn't really a problem of uncertainty. It's just for the fact that we've linearized the system. We couldn't account for that nonlinearity, so we just sort of pretended it didn't exist, and maybe we'll shuffle it off to that delta, right? So we've got our nominal system, which is linear, and maybe we connect it through a delta here, which has some nonlinearity in it, perhaps. So if you remember our pendulum, right, that was mgl sine theta, right, and we linearized it, and then the nonlinear part was theta minus sine theta or something like that, right? In this case, I've got another example, so I won't talk about the inverted pendulum, which is an interesting set of nonlinear dynamics, and there are lots of interesting sets of nonlinear dynamics. Unfortunately, linear systems are rather boring, or fortunately, because it means we can control them. Anyway, so this is it. It's the Rayleigh equation. It gives a nice limit cycle. So if you simulate this thing starting from a point, the equilibrium point is unstable. The trajectories will diverge. So even though the equilibrium point is unstable, trajectories diverge, but they don't go off to infinity. In fact, they go to this manifold or this circle. I don't know. It's not really a circle. It's sort of an elliptical thing there. A limit cycle is what we call it, because the trajectories converge, and then once they get there, they sort of stay on that limit cycle. And even if you start outside the limit cycle, you'll converge to the limit cycle and go on. That's called a limit cycle here. Right. So obviously, this system has an equilibrium point at 0, but it's not a stable one. But the system is not actually unstable because the trajectories converge to this equilibrium or this limit cycle, and so this is sort of a weird case. So how do we deal with these kind of problems? Well, typically, of course, we linearize them, right? And then we take the nonlinearity and we put it off in that delta. This example here is a slightly different approach, where here we've got our nonlinear system, and there's only one term which is nonlinear, which is this one right here. So actually what we're going to do in this example is actually take that whole nonlinear term and put it in the uncertainty block, right? So how do we do that? Well, we just write, I think we're going to make x2 the x2 equals y, and then x1 equals y dot, and then so we've got y double dot equal, well, move that up a bit. We have y double dot equals 2 zeta, I think that's zeta, y dot minus 2 zeta alpha y dot cubed minus y plus u, right? And so we put this, we ignored this part right here for now. We'll put it in a variable or signal q, right? The part coming out is p and the part going back in is q. So we'll make q equal to, what is it, x1 cubed, right? So we ignore that part there, and we put the rest into a sort of state space form, right? That goes there. This bit goes there. This bit goes right there, and of course we got this bit right comes down to here. And then of course we got the nonlinearity, right? So we made q equal to x2 cubed, and then we have the term which multiplies q right there, and that bit goes down there. And so we've got a linear system here. So this is the linear system coupled to a nonlinear system, which is this part right here. All right, so we put it in the LFT already, right? So this is the LFT representation. Right. So to some extent, we've sort of done the same thing we did for parametric uncertainty, but we did for nonlinearity here. This is, unfortunately, it's not as easy to deal with, well, we haven't actually solved any problems, although we put certain problems in the LFT. We haven't solved any problems using the LFT. Unfortunately, for nonlinearities in that delta, it's a little bit harder to solve problems, but there are things we can do. First of all, right, it's hard to deal with things like use tools like the small gain theorem, right, for these nonlinearities, because nonlinearities tend to not satisfy small gain conditions. For example, if you have the output of the system, which is Q, or that nonlinearity, delta P, well, that Q is never going to be less than some finite gain times the input of that system because of that cubic term, right? If you get P large enough, right, any K will be violated. So this is never going to satisfy a small gain condition. There are conditions it does satisfy, however. So for example, we can often put nonlinearities in sector bounds. That's not what we do here, however. Well, it's sort of what we do here. It does satisfy a passivity condition, however, right? So we can look at this, this integral, right, of the product of the input and the output. And the output, remember, is p cubed. So the product of the input and the output is p to the fourth, which is always positive. And so the integral of the input and the output is positive, so passive, right? Right. So is that going to help us? Well, maybe. Remember, we had passivity theorem, so we could, if we could make this thing passive, then maybe we could get something about the stability of the closed loop interconnection. But in any case, the main focus here is on just showing that these types of systems can be formulated in the LFT. This is not the only way to do it, of course. There are probably more intelligent ways to do it, in fact. But it does show that you can do something. The second class of things which we haven't really discussed too much are those unmodelled states. And so this slide and the next slide deal with the question of unmodelled states. As I mentioned in the introduction to this lecture, right, one source of unmodelled states is model reduction. So if you, it's a linear, you take a system and you use the Bode plot to identify a transfer function, right? That gives you a transfer function g hat of s, but that will have a very high degree. So you identify certain the states which are least important, and I'm not going to talk about model reduction here. It's a very interesting topic. There's several forms. I encourage you to look up, say, balanced truncation, which is my favorite, or Hankel, what is it? Hankel model reduction. I forget what the actual form is. Hankel is in there, right? So there's lots of ways of several ways of doing. None of them are particularly rigorous, I've got to say, but there it is. But in any case, right? So the idea is, right, there are some states which don't really contribute very much to the map between the inputs and the outputs, right? So maybe x2, for example, is not as important if we cut it off. It's not very, that doesn't change the size of the map from the input to output very much. Okay. So often we just get rid of it. We just ignore x2, say it's 0, and then we have a much simpler, much smaller set of dynamics. And there are very often lots and lots of states in these these system identification tools which don't really contribute much to the input-output maps. However, right, they contribute something, and you can't really bound that contribution as an exogenous input a priori. And so we have to think of these, the effect of these states as dynamic uncertainty. Right? And so how do we capture the effect of these states? The answer is, of course, we put it in the LFT. We put it in the delta, right? We have a smaller nominal system, P, which has an output signal P of t, which goes into our delta and which gets fed back through Q of t. Right? So we have an equivalent representation of the system. This is a smaller system. The entire system is the same, but the nominal part is smaller because it only has the states x1 in it. So how do we construct this equivalent representation? Well, right, if we just look at the dynamics of x1 dot, right, there's the nominal part, right, a11 x1 dot. That's the one you really want to capture. The effect of w on that state, right? That's there, and then everything else gets input through this p here, right? And I haven't. Well, you might have a matrix in front of p, but I haven't really bothered making this very sophisticated. So it just that's what it is. So what is p? Well, p is all the terms that are no longer included in this representation. Specifically, a12 times x2, right? So how do we get x2 if it's no longer in the system? Well, that's what's x2 is going on, is what's happening here, right? x2 dot equals up in that uncertainty block, right? So x2 dot, right there, that's what's going on in the uncertainty. The dynamics of x2 dot, right, are given at a22 x2, right? I'll just highlight that, x2. That's what's going on there. And then, of course, right, there's some disturbances to those dynamics, some inputs to those dynamics, specifically the effect of x1, and of course the effect of b2. So x1 is so both of those terms have to be output basically. So we need the extra terms here, right? We need plus a21 x1 plus b2 w of t. Again, there's several ways of doing this. I've chosen just, it's not a very efficient actually representation because it moves more information than it really should. So I've chosen to make the output from P this A12 terms. So that's this bit right here, right? Actually, I've done this wrong. No, sorry. I've my bad. I mislabeled things. That's my apologies. I've actually output the Q here. So instead of P, I shouldn't have done that because I should have made this P and made this Q. So that's sort of a typo on this slide. Or at least inconsistent notation. So sorry. So what I've done here is I've outputted both X1 and W into this signal Q, which I've now relabeled as P, so I'll just keep it as P. So that output signal is both X1 of T and W of T. Right. So everything you need to know to get these extra terms here. Right. Right. And then, right, those two terms then are filtered, right, through A21, right, multiplies the first term, and B2 multiplies the second term here. So they both come into the dynamics in this way. Again, right, this wasn't a very clever one. I really shouldn't have, should have done it more efficiently, making that output signal itself A21 X1 plus B2W. That would have been clever, but I didn't do it, sorry. Anyway, either case, right? You get the same set of dynamics going out to the to this uncertain system. Then you have the X2, the dynamics of X2, that produces X2, obviously, and then we can just the output for that system is A12 multiplied by X2Q, and so now the dynamics here are we recover the original dynamics A12Q. So P becomes A12Q, which is equal to A12X2 of T. Right. So again, this is an equivalent LFT representation of the full system, where those state dynamics for X2, which presumably are actually there are more states in X2 than X1, but we think that they don't matter very much, so we put them in the delta. And then if they really don't matter too much, right, we can just bound the norm of them, right? So we figure out how much, what's the size of the map between the inputs and the outputs here, and we can say that that has some finite H infinity norm, which we know. And then we can design controllers for this system, knowing that there's a little bit of uncertainty in that delta, unstructured uncertainty, or more or less unstructured uncertainty. And we just have a norm bound for it. So then we can apply things like small gain in this very simplest case to show that whatever controller we use then recovers stability after we've designed the controller. Or we can, as we'll see in lecture 14, we can do a little bit better than that. We can design a controller which inherently is optimal for all deltas with norm less than 1 or 0.1, or actually 0.01 if it's actually if the system identification as the model reduction tool is particularly good. Okay. But in any case, right, this system has states, right? It's the same system, but those are the states we don't want to worry about, right? So we've just bounded their size. The next interesting example, right, is again a sort of structural uncertainty, sort of time-varying parametric uncertainty, depending on how you look at it. But it's a very common case, and that's gain scheduling. Right? This is very common when you have things which operate in different which have different operating conditions. So you say, for example, an airplane, right? An airplane has to be controlled in lots of different environments, right? It has to, at high altitude, say height of greater than, say, 30,000 feet, for example. It may operate at a height of greater than 1,000 feet, right? And the density of the air and various other conditions going on there are going to be very different. So the parameters in our model are going to change continuously over time. And so a typical approach then is to design a different controller, like a controller for low altitude, and a controller for high altitude. And then you switch between them when you get to, say, h equals 10,000 feet or something like that. Or you might have lots of controllers. You might switch at 10,000 feet and then switch again at 20,000 feet, right? Things like that. Or switch at 5,000 feet, right? So you might have a whole bunch of different controllers, each optimized for a different operating condition, right? And then what's going on is that when you switch between those controllers, right, you get some dynamics which are not modeled in the linear model for any of those operating conditions, right? So here we have this logical switching. So if the height gets below 3,000 feet, for example, you have one controller, and if the height is above 3,000 feet, you have a different controller, for example, right? I think this is actually an image from the book. So you're trying to shoot down the airplane. I don't think that's a great idea, but so we'll just think about airplanes and not shooting them down. Thanks. In any case, right, that switching dynamics, very common for gain-scheduled systems, and it's not just height, right? Different velocities require different controllers because the dynamics change significantly at different velocities. Changes with Mach number, right? The switching, the transition between one controller and another, right, creates instantaneous changes in the dynamics as you move below or above this threshold. And in the worst case, what can happen is that if you're not careful, right, the switches, when you switch above, when you get above a certain height, it can push you back down to that height. And when you get, because airplanes are zero, what do you call it? Are non-zero, I forget what they're called. Anyway, they tend to go down before they go up. That's my point. So typically, if you want to make an airplane go up, you actually push it down to get a little speed out. It tends to push the aircraft down slightly because you push the aileron up. And anyway, so airplanes tend to go down before they go up, and so you can get this situation where when you switch, you suddenly are pushing in an opposite direction, which pushes you below the switch again, or the switching altitude. And then, of course, once you get below, it switches the controller again, which may push you back up to that altitude, and so you can get these they're called xenodynamics. We may get to that very late in this course, but we're not getting to it now. So you can get weird things happening, basically, if you don't account for these switches. And gain scheduling is a very, very commonly used tool, and so it's the uncertainty introduced by switching between these controllers can cause things to happen which you don't really want to happen. Now, technically, these switches can be modeled, right? You don't have to treat them as uncertainties. You can model them using hybrid system approaches, and those we may talk about them at the end of the course, or we may not, depending on how far we get. But in any case, if you don't want to think about them as hybrid systems and introduce more complicated models, you can think of them as time-varying parameters, right? So that you can think of the A of t and B of t as time-varying, and they can vary within any of our set points right here. Right? So one for h equals 1, one for h equals 2, one for h equals 3, one for h equals 4, and so forth. And so you might model this as polytopic time-varying uncertainty, right? So you prove stability for any of these operating conditions, or arbitrary switching, so they can switch at any time. Or you may take a different approach and just model the hybrid dynamics. But of course, we're doing robust control at this moment, so we tend to think about it more as time-varying parametric uncertainty. And this is the gain scheduling scenario is a very common source of models in robust control, especially for that parametric uncertainty case, time-varying parametric uncertainty. Another example of unmodelled states is the case of delays, right? We talked again about this at the beginning of the, actually I think I gave that, what color did I give that? I think I gave it pink. We talked about this again right at the very beginning of the lecture, where there's maybe a communication delay between your controller and your UAV, right? So communication delay forward, communication delay back, right? And delay actually, right? It's, well, if you write the transfer function of it, it looks like that. It's not a rational term. It's not a rational transfer function, which means if you model it or you approximate it as a rational transfer function, if you take a rational approximation, you're going to get a rational function with infinite degrees on your numerator and denominator. D goes to infinity for those degrees, which means if you come up with a state space model, then you have an infinite number of states. Right. So obviously, I guess you could think of it as model reduction, where you just ignore all the delayed states, but so that's one approach. Again, right, we're concentrating on the LFT, and so specifically for the delay, what one can do, right, is take that delay, right, and put it in a channel, right? So if we're talking about the LFT, we have our nominal system, P. We have our uncertainty, right, which where we'll put in that E negative tau S transfer function. And so what goes into that? Well, so this is the delayed term, right? So what goes to that, so let's model our states here. Right? We have P going out, modeled it correctly this time, not Q. So P is the state itself, right? It gets shuffled off here. So X of T goes into the uncertainty, comes out as X of T minus tau. Right, so what comes out is X of T minus P of T minus tau, which is X of T minus tau, and then gets put back into the system, right, through that, actually that should be a 1 there, a matrix 1, right, so that's X of T minus tau. Okay. So we've equivalently represented the system as an LFT, and now we can do things like, for example, the delay, for example, the transfer function. If you look at that, right, what does it look like in the frequency domain? Well, if you draw its Nyquist plot, for example, it's just a circle, right? And so, for example, the norm of the transfer function, the H infinity norm, is just 1. It's exactly 1 in this case. And so you can use things like small gain to analyze stability of the closed loop. This, this is a pretty naive approach, what I've done here. People typically try and give it a little bit more properties than just small gain, but this is nice because it will work for any delay, right? So even if your delay is infinitely large, this modeling as small gain will work. Right? So again, a way of taking the parts we don't want to deal with and putting them in a delta, so that we don't have to think about them too carefully, and then interconnecting it back into the original system, or the uncomplicated system, the linear system, linear finite dimensional system. So that concludes sort of our brief survey of sources of uncertainty, and of course our overview of how to put those uncertainties into the LFT framework. However, before we get started working with the LFT per se, which we're going to do in, actually, we're not going to do it in the next lecture. We're going to do it in lecture 14, right? There are certain circumstances where we don't need the LFT, and in fact, there are certain circumstances which might actually be advantageous not to use it. So remember the LFT right here. In the case of parametric uncertainty here, right, we put those uncertain parameters delta 1, delta 2, delta 3 here. Right? Where that, in most of these cases, right, that uncertainty has some structure. It's not completely black box, right? And unless you exploit the structure of this uncertainty block efficiently, then you're going to get conservative results, right? Inaccurate results, right? In certain cases, we can avoid using the LFT, and if that works, that's great. Because in certain circumstances, we can get less conservative results, I should say. And then we're not, it's sort of hand wavy, right? Sometimes they're less conservative, sometimes they're more conservative. But there are certain special cases which are not conservative at all. Not many of them, but there are a few. And so let's consider a couple other cases. So specifically, time-varying parametric uncertainty. That's a good one. It's a good one because we can handle it in certain important cases. So in particular, in the case of where the uncertain parameters are polytopic, or where the uncertain parameters lie in an interval. And I emphasize both of these apply to the time-varying case. Yeah. So just remember what these are, right? So here, interval uncertainty. So we've got a nominal plant, nominal system matrix, nominal. And then we have some perturbation of that. And the perturbation, right, can be either polytopic or interval. And so let's take the interval case. So we have certain parameters. These may be those delta m's and delta c's, for example, and delta k's, for example, where we have a model for how those parameters fit into the nominal system or fit into the overall system matrix, right? So this is A of delta m, delta c, delta k, and so forth, right? So we have some model for how those fit is, and that's what defines these AI matrices for each individual parameter, right? Notice it has to be linear, right? They have to enter linearly. There's no rational way we can do this rationally, as in 1 over the delta, for example. And they can't multiply each other, right? You can't have delta 1 times delta 2, right? That can't appear, right? So we can handle that in the structured in the LFT. We can't handle that in this particular case, unfortunately. No multiplication. Okay. It doesn't seem like that's so big a deal, but actually multiplication is often quite important. In any case, right, there's once we've agreed to this sort of additive linear representation, additive linear, then there's two subcases of that, right? The first is interval, right, uncertainty, where each parameter lies has a minimum and a maximum value. And the other case is the polytope. And we've already talked about the polytope a little bit, right? So that this often comes when you take various measurements of those parameters and you assume that the actual values can lie anywhere as a weighted average of those measurements. Measurement 1, measurement 2, measurement 3, and so forth, right? Okay, so that's the other case, the polytopic uncertainty. And then, right, the weighted average of all of those measurements is called the convex hull, and I think that's something we haven't defined before. So it's a definition, convex hull, of those measurements, right? These are the measurements. And so now our uncertainties are actually these alphas, right, which are actually deltas, I guess. But delta lies in this set. And we can make that time varying by allowing these parameters to vary anywhere in our set points. So say, for example, if the airplane is flying between various operating conditions, we just constrain it to lie somewhere in the weighted average of those operating conditions. So polytopic and interval uncertainties are two special cases. And I emphasize, right, that it has to be additive and it has to be linear, that representation. So to give an idea, a case where this actually works, right, is back to our mass spring system. It only works actually through luck, it turns out in this case. So if you remember, right, here's our dynamics, right? And we came up with a state space representation right here. And first of all, you look at this, and there's no way you think that this can be represented as, right, A1 delta M plus A, or A naught, don't forget the nominal one, plus delta A2 delta C and A3 delta K, right? Because there's M inverse here, and there's M inverse here, and it multiplies C, and so there's actually no way that we can represent this A matrix in this additive linear form. Fortunately, however, there's a variable substitution trick in this particular case, right, that we can use. So call it a variable substitution trick. Where we declare 3 new uncertain parameters. So specifically, we make this parameter delta 1. K is delta 2. Forget the assume we're talking about the uncertainties in these parameters. And the third one is C over M delta 3, right? So we make those are our 3 variables, and fortunately they vary independently. Or we given delta 1, delta 2, and delta 3, we can come up with they uniquely define K, M, and C. So this is an invertible transformation, right? Delta 1 equals 1 over M, delta 2 equals K, delta 3 equals C over M, right? So clearly, like given M or given delta, you can find M is 1 over delta. Given K, well, there's no problem there. And then given delta 3 and M, which is already found from delta 1, you can recover C as well, right? C equals delta 3 delta, or divided by delta 1. So it's invertible, so we can actually do this variable substitution. And now we can put limits, interval constraints, on these new variables. Delta 3 equals, and then K doesn't change at all, right? Delta 2, right? So interval constraints on the new variables, which are equivalent to interval constraints on the original variables, which appear nonlinearly. Right? Emphasize, of course, this doesn't always work. This was we were lucky here, right? If we added more complicated terms, or if M appeared in a different term, or in a different variable, or didn't multiply C in another, it wouldn't work, right? So we'd have a problem. Fortunately, in this case, however, it works. Right? It doesn't always work, though. So it's affine in the parameters, right? We've done a variable substitution, change of parameters, which has become affine in those parameters, right? If you can't do this, go back to the LFT. There's no alternative. However, in this case, we can actually get slightly more accurate results by doing this variable substitution trick. Right, so finally, I'll just sort of conclude with by mentioning that all of these results actually apply directly to the discrete time case. Right? So specifically, right, if you have uncertainty, and this is the parametric case, if you have uncertainty in your discrete time dynamics, xk plus 1 equals a xk plus b wk, right? If you have uncertainty in these, right, and you can represent this as an LFT, right? If you can write it out, you can apply the same steps that we went through for the continuous time to the discrete time case, using this fractional transformation for the closed loop representation of the system. Right? So those results apply. Similarly, for the polytopic case, we can, or the interval case, if we can represent the system parameters in an affine linear way, right? So affine way, in that there's the uncertainties don't multiply each other, and they just add together, right? So there's no 1 over delta terms or delta 1, delta 2 terms or anything like that. So again, just the same case as in continuous time, but it also, I should mention, works for discrete, and we'll have some, I'll just briefly mention some in the next lecture, some results on discrete time case, but they differ so slightly from the continuous time case that it's not really worth our time going over them again for the most part. So to conclude now this lecture on Introduction to Uncertainties, I hope I've given sort of an impression, which is a correct impression, that the field of uncertainty is uncertain, right? That there are lots of cases of things you didn't model, right? Lots of types of things which weren't included in the model. So emphasizing there's dynamic uncertainty from unmodelled states. There's parametric uncertainty from uncertain parameters. This in the LFT. If you have parametric uncertainty, you can also have alternatives to the LFT, including, now I need a new color. Actually, I should do that purple before I switch, right? So these are LFTs here. Representations, LFT representation, LFT. And here we put LFT here as well. So there's alternatives to LFT, which is the polytopic and interval representation. The uncertain parameters may be structured. In fact, they often are. Or they may be unstructured. Another color. They may be structured, or they may be unstructured. And that refers to, of course, whether they have that diagonal term with zeros on the off diagonal, or whether it's a full matrix, just delta, right? Furthermore, these uncertainties may be time varying, or they may be static, right? So they may be static here. They may be dynamic, right? Time varying, which is actually sort of one of the orange case, I guess. That's what I was using for there. Right. So lots of different cases, which is unfortunate because it means that the field of robust control is a little bit fragmented. So it's hard to sort of summarize the core of robust control in 3 or 4 lectures. But we'll do our best to hit the highlights of the problem. And in particular, these 2 are highlights. They're very, very important special cases. So we'll go through those in the next lecture. And then following that, we'll come back to these cases in lecture 14. So we'll try and hit the main results for each of those cases, when we can design controllers, when it's not possible, and so on and so forth. So I hope you'll join me then in our next lecture, where we consider these latter 2 cases, the polytopic and the interval parametric uncertainties, and then coming back in lecture 14, of course, when we return to the LFT. All right, so I'll call it a night.